Our journey of creating new math continues as we uncover the rise of trends in the literature and the problems with their calculation. We've discovered the emergence of trends and will continue to create new math for them. First, we must understand why we dedicated a framework for local rates, differential calculus, but not local trends.
Math frameworks are developed based on the scientific community's needs and applications in various fields. The concept of trends wasn't as useful before as it is today.
What would a trends framework be good for? First, we'll benefit from efficiency because the current applications are only sometimes using trends most cost-effectively. Computability. Differentiable functions are incredibly sparse in the set of continuous ones. It would be helpful to have a tool that measures trends independently of differentiability and, even better, continuity. Applications are amassing. As mathematicians, we should strive to build a theory that models them correctly. Another reason is being able to complement the mathematical branch about rates with a dedicated branch for trends. These are two different ways of measuring a change. Also, the trend theory bridges applications in discrete domains with continuous ones. This reflects Laszlo Lovasch's sentiments in his article, One Mathematics.
We have to do our best to bridge these gaps.
We'll invent the new framework as follows. First, we suggest a new method in calculus to capture local trends. Then, we discuss the applicability of the new idea in discrete and continuous domains. We'll illustrate at a high level how we could build a theory based on the new concept. We'll discuss how our approach fits into the terrain of current mathematics. Imagine you view a dashboard of a driving car. Say, you want to answer a simple question. Is it driving forward, backward, or just standing in place? Would you first use the speedometer to answer that question? Or would the gear stick indicator be enough? Now, let's take this analogy back to calculus and see if we can calculate local trends directly without first going through the calculation of the derivative. Here is the sign of the one-sided derivative, and let's put it in detail. What if we push the sine function into the limit process? It's a wrong transition. The sine function is discontinuous at zero. Therefore, it's generally wrong to switch the limit and the sine function. But bear with me for a second. After this transition, we can now suddenly cancel out the h in the denominator, which turns into a plus or minus sign based on the side of the limit. This last transition yields a new trend operator, different than the derivative sign we started with because of the inequality along the way. Let's compare the trend calculation using this operator with the derivative sign. Consider the right-sided derivative of y equals x squared at 0. The function seems to trend upwards. If we define the trend by derivative sign, it is zeroed, yet graphically it rises there. To rectify this, we introduce the trend operator distinct from the rate, which is +1 at x equals 0. This operator amounts for the persistent +1 direction of change, regardless of proximity to 0 and even in the limit, due to the discontinuity of the sine function at 0. Thus, it accurately defines local trends for functions with zeroed or undefined derivatives. Our new operator extends its application to broader scenarios. Using the analogy of three balls in calculus, we indicate that while differentiable functions are continuous, neither continuity nor differentiability guarantees a trending function according to our new definition. We provide examples demonstrating trending functions that lack continuity and differentiability, and the opposite. Local trends may appear in nowhere differentiable functions like the Weierstrass function or when the function's limit is undefined. However, as expected, the trend operator fails to capture the trend in significantly oscillating differentiable functions. This new trend definition methodology is similar to the derivative. In the latter, the slope of a second turns into a tangent as the points approach each other. In contrast, the former calculates the trend of change in an interval surrounding the point at stake. It then deduces the momentary trend of change from it by applying the limit process. Both tools make delta y informative by discretizing it. Otherwise, it would be zeroed in the limit process. Now that we've covered some advantages of the trend operator in continuous domains, It's worth noting that sparing the division also addresses problems we previously discussed in discrete ones. For example, removing the division may spare up to 20% of runtime to AI algorithms where the division is significant relative to other atomic operations. It may also reduce the risk of overflow, gradient explosion, and redundancy. Overall, it makes algorithms in discrete domains more efficient and accurate. Reflecting on Leibniz's statement,
Everything that is possible demands to exist.
let us extend this idea to calculus, a field he co-founded. His axiom inspires us to delve beyond the conventional and explore new possibilities. Today, we introduce a new calculus definition stemming from the trend of using trends, a case that, by Leibniz's principle, demands its existence and exploration. So let's explore it together and see how it can enhance our understanding of calculus. Here is the definition of the new trend operator. We denote it by a semicolon to emphasize its semi-discrete nature, combining the discrete sign function and the continuous notion of the limit. We call this operator the detachment operator, because when applied to functions, it detaches them at their extrema points, resulting in a step function, representing the original function's monotonicity regions. To recap, we began with the derivative sign, inserted the sign function into the limit process, and it resulted in a new operator.
Next, we'll take an exciting journey into the world of semi-discrete calculus. Stay tuned as we explore this fascinating topic.